Now let us understand the concept of escape velocity. To understand escape velocity, watch this exciting video. It is quite interesting and I hope you will enjoy watching it. So learn escape velocity through this video. Thank you.
RoboMate Plus, India's largest curriculum-based study app. Download the app now.
I think you all remember making this paper plane as a kid because we made this paper plane with a lot of hope, and we actually thought that when we would throw this, it would go soaring into the space. And when we threw this paper plane, for a microsecond we actually thought it would go into space, but finally the plane came down. And when it came down, we cursed gravity and we actually hoped it would not exist. But then as we grew up, we realized gravity was not that bad after all. Even simple things like drinking water would be so difficult without gravity. I know the intelligent minds must be thinking, of course you can drink water with a straw, but that would make it so difficult and there would be one thirsty human race. But what if I wanted to take this object and send this object into space beyond the Earth's gravitational influence? What kind of a velocity would be required to send this object beyond the Earth's gravitational influence? That kind of a velocity is called escape velocity. So I have this magical bat here, and I'm going to set this magical bat to Dhoni's highest sixer ever, and that was in New Zealand, 120 meters high. Now here comes the ball, and I hit it, and it goes 120 meter high. But then finally it has to come down because of the Earth's gravitational influence. I think you all must have heard about Concorde plane, one of the fastest moving objects. It traveled with a speed of 2,200 kilometers per hour, which is around 600 meters per second, faster than sound. And now the ball comes, and I hit the ball with the speed of Concorde plane. And you can see the ball is going very fast and it breaks the speed barrier, and there is the sonic boom. But still, the influence of gravity acts, and finally, again, the ball comes down. Let's take this to the next level. I'm going to put on the setting of the kind of velocity which is required while launching of rockets. The ball comes and I hit, and you can see the ball is going, and finally it goes and it begins to now orbit. Now when it is orbiting also, remember that even when an object is orbiting, it is still under the influence of Earth's gravitational force. Now why is this object moving around my hand? Of course, because of the force exerted by my hand on this object. Similarly, if you are seeing that object orbiting around the Earth, it is because of the gravitational influence of the Earth acting on that object. Now I want to send an object out of the influence of Earth's gravitational force. So let us see how that is possible. Now I'm going to set this particular bat with a speed of photon, which travels with the speed of light. Now the ball comes, and the ball is traveling with the speed of light, and you can see the ball continues to travel, crossing infinity. Now I don't want this to happen. What I wanted to happen was the ball should go and stop at infinity. So I'm going to take this bat to the infinity setting to send this ball to infinity. And here the ball comes, and I hit the ball, and you can see the ball is going, and it continues and continues, and finally the ball goes and stops at infinity. So that means it has escaped the Earth's gravitational influence. Now the velocity with which I hit the ball is called as the escape velocity.
Thank you for watching this video lecture. To watch more such interesting videos, attempt tests, and to get instant analysis, download the RoboMate Plus app now.
Hello folks, it seemed amazing to fly paper rockets as children. Well, as children, it seemed very hard to make that rocket fly up very high, far and far away. It's all due to gravity that never let it happen, right? Well, come on, let's find a way to fix this problem. In this video, we shall discuss about escape velocity and what would it take to escape from the gravity of the Earth. So, why the wait? Let's begin. Let's say we launch a rocket from the surface of the Earth. It will go to some height and eventually come down. But what if we launch a rocket such that it never comes back to Earth? How do we do that? Let's find out from the point of view of law of conservation of energy. According to the law of conservation of mechanical energy, initial energy EI is equal to final energy EF, where we neglect the external interactions of the rocket. When we fire off this rocket, it has some initial velocity, so it has some initial kinetic energy represented by Ki. The final kinetic energy is represented by Kf of the rocket. Since the rocket is in the gravitational field, it has some gravitational potential energy as well. Therefore, Ki plus UGI is equal to Kf plus UGF, where UGI is the initial gravitational potential energy and UGF is nothing but the final gravitational potential energy of the rocket. The kinetic energy of the rocket is given by half mv square and the potential energy of the rocket is given by minus gmm by r. Now substituting these values, we get half mvi square minus gmm by ri is equal to half mvf square minus gmm by rf. Let's say we fire a rocket from the surface of the Earth whose initial distance is given by ri to a far off place, say infinity, then the distance rf becomes equal to infinity. We are trying to find minimum velocity with which we can launch the rocket such that there is no excess velocity at the end. That is, Vf is equal to 0. So we get half mvi square minus g m into m divided by ri is equal to half mvf square minus g m into m divided by rf is equal to 0. Because Vf is equal to 0 and Rf is equal to infinity. Therefore, we get half mvi square is equal to gm into m divided by ri. On cancellation of m on both the sides, we have vi square is equal to 2 into gm divided by ri, or vi is equal to square root of 2 gm by ri. This vi is nothing but the escape velocity, which is defined as the minimum velocity for a free object to escape from the gravitational influence of a massive body. So if we consider the distance Ri to be equal to the radius of the planet, then we get V escape is equal to square root of 2 gm by r, where g is the universal gravitational constant and m is nothing but the mass of the planet. Substituting these values with respect to Earth, we get the escape velocity V escape to be equal to 11.2 km per second. Thus, for our paper rocket or any other object to escape from the surface of the Earth, we need to provide the escape velocity equal to 11.2 km per second. Let us